If we take a look at the molecule carbon dioxide and we were to draw its Lewis structure, we would see that it has polar covalent bonds, but it's a non-polar molecule. So let's look at its structure really quickly here. If we draw out its Lewis structure like this, there's two lone pairs of electrons on the oxygens, and then the carbon has two double bonds. If we draw in bond dipoles, they point towards the oxygen because the oxygen is more electronegative. So it has polar covalent bonds, but overall it's nonpolar. So why is this the case? Well, polar molecules need to have a positive end and a negative end. And if we look again at our carbon dioxide molecule, bond dipoles are pushing both out towards the oxygens. If we also recall, its shape is linear. And so this is essentially a tug-of-war game that nobody is going to win because both of the oxygens are pulling equally on those shared electrons, and no one's going to win this game. So there's no actual end that has a positive end or a negative end. Overall, both of those bond dipoles, we would say, cancel each other out, and so it's nonpolar. So how do we then take what we know and figure out whether a molecule is polar or nonpolar? Or essentially, how do we determine molecular polarity? Well, the first thing we're going to do is we're going to draw the Lewis structure because everything centers on the Lewis structure. And then we're going to draw the VSEPR shape diagram for the molecule because we need to know the shape in order to know how the bond dipoles are pulling on all of the elements in the shape in order to then determine does it have a positive or negative end or not. We're going to use electronegativities and we're going to draw in each of the bond dipoles. So we can use the delta plus, delta minus, or I would rather we draw in our bond dipoles, remembering that this end with the little tick is our delta plus end, and the other end is our delta minus end. So those are our bond dipoles. We need to know what's happening with each bond before we can predict what's happening overall in the molecule. Now, if the bond dipoles cancel, and we have to think about this in three-dimensional space, then the molecule is not polar, or we would say it's non-polar. And if they don't cancel, then the molecule is polar. So let's work through a couple of examples. Our first example is NH4 plus, so our ammonium ion. Just kind of looking at the number of electrons, we have 5 valence electrons for nitrogen, 1 for each hydrogen, so there's 4 more there. So that's 9, but because of the positive charge, we have to take away 1, so we should have 8 electrons in our Lewis structure. We do a central atom, do a bond to each hydrogen, and those are your 8 electrons. So we're just going to finish this off with square brackets and a positive charge. Now looking at the nitrogen has 4 bonding pairs and 0 non-bonding pairs. So this is a tetrahedral shape. So we can go ahead and draw in the VSEPR shape. So it's going to have 1 hydrogen up, 1, and we're really stressing the angles going out to the side. We're going to have a wedge, and then the other one angled down to the right there. Okay, just going to put square brackets around this again because it's good practice. It's an ion. Now we need to do bond dipoles for each. If we were to look up the electronegativities, nitrogen is the more electronegative atom here. So each of the bond dipoles is going to point towards the nitrogen. Now we need to remember in this molecule when we're determining whether it's polar or nonpolar that this has three-dimensional shape. So the three hydrogens around the bottom are in a trigonal pyramid kind of shape. And so they're each going to be pointing up, but they're pointing up at different angles, or they're at angles themselves. And so really what we kind of need here is vector addition. And if you don't know what vector addition is, it's okay. We're just kind of taking a look and seeing if we added up all three of those. Generally what's going on is that they're going to equal a bond dipole or a dipole pointing upwards that's going to cancel out the one coming downwards. So we would say that they cancel each other out. And so this molecule is nonpolar. Let's look at another example then. So we're going to do the NO2 minus ion. Let's tally up our electrons first. So we've got 5 electrons. We have 2 oxygens, so that's 12. And then we need one more for the negative charge. So that's 18 electrons total. Let's put our nitrogen in our middle, create bonds to our oxygens. So that's 4 taken up, fill the outers. So that's 16. One more pair on the nitrogen makes 18, but our nitrogen is not satisfied, so we're just going to create a double bond with one of these oxygens. And we'll fix that up there, and there we go. There is our Lewis structure. Remember, we got a double and a single bond, so this structure has resonance and actually has delocalized pi electrons as well. All right, so looking at this, we count the double bond as one bonding pair. So we would say we have 2 bonding pairs and 1 non-bonding pair. So this is based on trigonal planar shape, but it's our bent or our V shape. So if we were to draw this out in our shape, we're going to have our nitrogen with our lone pair electrons on the top. We're going to have one oxygen going out that way and our other oxygen going out that way. Okay. We don't need to put all the pairs of electrons on the oxygens because this is a VSEPR shape. Now, bond dipoles going in here. The oxygen is a little bit more electronegative than the nitrogen, so they're going to point out this way. And if we take a look at those 2 bond dipoles, overall, if we add the 2 together, it's going to result in a dipole that's pointing downwards. So what does this mean? Well, it means that this molecule overall has a slightly positive end on the nitrogen end and a slightly negative end on the oxygen end. So overall, this molecule is polar because those bond dipoles do not cancel. So those are a couple of examples of how to come up with molecular polarity. That's it for this video. We'll see you in the next one.